Now that you've been introduced to the quantum numbers, we're going to see how we can use those numbers to identify a highly probable location or address for each electron in an atom. We could begin with the Aufbau principle. You'll see there are three kind of governing rules for where an electron is most likely to be found. And the Aufbau principle states that electrons are going to be added one at a time from the lowest energy level to the highest energy level, and that an orbital, as you saw earlier, can only have at most 2 electrons. So it can have 1 electron or a maximum of 2 electrons. And here's a couple diagrams to help you to help explain the Aufbau principle and the filling order for electrons. So as you start filling electrons moving across the periodic table, when we look at hydrogen, hydrogen atom only has 1 electron in it. That 1 electron is going to be located in the lowest possible energy level, which is the 1s orbital, and that would be the ground state location for that 1 electron. If we go to helium and add a second electron, that second electron for helium will also be located in the 1s orbital. If we move to lithium, where we add another electron, lithium has 3 electrons. It would have 2 electrons in the 1s orbital and then 1 electron in the 2s orbital. And you can see that the energy levels increase with that principal quantum number 1, 2, 3, 4, and it can go on beyond that. And that as we move up in energy level, we start adding more and more orbitals and sublevels to contain those additional electrons. The Pauli exclusion principle basically states that no 2 electrons in an atom can have identical quantum numbers. So essentially, no 2 electrons can have the same address. This diagram here shows the spin of an electron, of 2 different electrons within 1 orbital. So if an orbital has 2 electrons in it, they're going to have opposite spin, which is defined by the 4th quantum number that we did not really get into in the last presentation. Hund's rule basically states that electrons will space themselves as far apart as possible by occupying all available vacant suborbitals before they'll pair up. This is due to that repulsion factor. Remember that electrons are negatively charged, and like charges tend to repel each other, and so electrons are going to want to be as far apart as possible. And so you'll see that what happens is electrons will actually will reside in an unfilled orbital before they will start to pair up inside of an orbital. So there's 2 diagrams there. One shows the orbital diagram for carbon, and the other is the orbital diagram for nitrogen. And you can see that for carbon, it has a total of 6 electrons. The first 2 electrons are in the lowest state in the 1s orbital. The next 2 electrons are in that 2s orbital, or most likely to be found in that 2s orbital. And you can see that within those 2 orbitals, the 2s orbitals, that those electrons show opposite spin with an up arrow and a down arrow. When we get to the 2p sublevel, there are 3 possible orbitals for the electrons to occupy. And notice that the remaining 2 electrons will each occupy a separate orbital before they start to double up within 1 orbital. When we get to nitrogen, you can see that we're adding 1 more electron, and that 7th additional electron occupies again an empty orbital before it pairs up with another electron in an orbital. A good analogy for how these electrons fill these available orbitals would be if you were to get on a city bus and look for a place to sit. Most likely you're going to sit in an available seat, the nearest available seat that does not have another passenger in it. We tend to just behaviorally wise, look for that empty seat before we would sit next to a total stranger. And in terms of energy, most people are more likely to sit in the nearest seat and not go farther than they have to to find a place to sit. And so likewise, electrons, rather than sitting with a stranger or another electron, will occupy the lowest energy available orbital that does not already have an electron in it. Once that 2p orbital is filled, as we see with nitrogen, when we move to the next element, the electrons will then begin pairing up inside of those orbitals. So to summarize these three rules, you have the Aufbau Principle, this Pauli Exclusion Principle, and Hund's rule. Electrons are going to occupy orbitals of lowest energy available. So they'll occupy those lowest energy orbitals before they start occupying higher energy orbitals. And remember that that's also known as the ground state for those electrons. No two electrons in the same atom may have all four quantum numbers alike. So the principal energy level is going to be different, or the sublevel letter SPDF will be different, or the orbital that they reside in will be different, or the spin number will be different. Okay? When entering orbitals of the same energy level, electrons initially occupy them singly and with the same spin. So as we saw in that last diagram, in that p orbital, the electrons were occupying an orbital by themselves, but they also had identical spin within those orbitals. So when we write the electron configuration, you'll see that you have three of those four quantum numbers listed. And the first number, which is represented by the letter N, is the principal energy level number. So that would be that number 1, 2, 3, 4 that corresponds to an actual period in the periodic table. The next what you'll see next is one of the subshell letters or sublevel letters, SPDF, and then there will be what looks like an exponent, which indicates the number of electrons that are in that sublevel, and that's represented by the letter X.